Bismillah ar-Rahman ar-Rahim. Alhamdulillah wa salatu wa salam ala Rasulullah. Welcome back. Today we're gonna draw the root locus for this control system. Okay. Let me write it again here in this slide. Okay. So given. Okay, this is given. OLTF, the open loop transfer function of a control system given as K, the controller, over what? S plus 1, S plus 2. This is the open loop transfer function, right? Okay. Find first he wants to draw the root locus. Draw the root locus. And then design K. Find K, the controller, K range for stability. Okay. So this is the objective, in fact, in control. Why we need control engineering? We need control engineering to design the controller. In this problem, we only focus on stability in this course, in fact. Okay. So this is very interesting example. All right. Solution. Okay. We always start from locating the poles and the zeros. So here, what I'm going to do, I'm going to draw the S coordinate system. Okay, this is the real part and this is the imaginary part, J omega. Good. So number one, this is very easy. Locate all the poles and the zeros. How many zeros do you see here? None. We don't have a zero. This is controller, not zero. Okay. Okay, so we have no zeros. We have only poles. What are the poles? Start from the smallest, P1, or the largest, sorry. P1 is 0. We have pole at the origin. P2 is -1. P3 is -2. Okay. Now you go to your coordinate system. Let me use another color. Let me use blue. And locate the pole. We draw the pole or mark it as an X. So we have a pole at the origin, X here at 0, and another X here at -1, and another X here at -2. Remember, we mark the pole as an X, and if we have 0, we mark it as a circle. Okay, O. So we have 0, -1, -2. Good. Let's go back. So in rule number 1, locate all the poles and the zeros. Okay. Rule number 2, number of branches. Or let me do this next, it doesn't matter. Let me locate the root locus on the real axis. If we have a root locus on the real axis, then it's going to be to the left of an odd number of pole or 0. Okay? It doesn't matter pole or 0. We start from the left and we counting, okay, not the value, counting. This is number 1. Pole or 0, doesn't matter, number 1. So number 1, it's an odd number, right? So to the left of an odd number, we must have a root locus on the real axis. So here, we must have a root locus on the real axis. You got it now? Okay, because this is an odd number, number 1. Number 2, not an odd number. So there must be no root locus here. Number 3 is an odd number. So there must be a root locus. There is no number 4, so it's going to infinity. The root locus here is going to infinity. And when you see a root locus that goes to infinity, we call it what? We call it a branch. This is a branch. Branch means very long. This is not a branch, it's an interval. This is a branch. Okay? Trying to draw it as best as we can. So let me write again, what did we do here? Root locus on the real axis, sigma axis, the real axis is on the real axis left to P1 and ends at P2. Left to P3 ends at, do we have a pole here or 0? No, so it ends at 0 at infinity. We call it 0 at infinity. If there is no 0 or pole, we call it 0 at infinity. I'm going to talk about it later, inshallah. Okay, number 3, also very interesting and easy rule. The number of branches of the root locus equal the number of poles minus the number of zeros. So, how many poles do we see here? 3. How many zeros do we see here? None. So how many branches we must have? 3. Already we have 1 branch, so we need to draw 2 more branches. Okay, clearly the branches will break away from this interval, from this root locus. One will go up and one will go down. How do I know this? Because this root locus already start from this pole and end at 0 at infinity. We don't have 0 here, so it will end at 0 at infinity. We will imagine there is 0 at infinity far away there. Remember, the root locus always, this is also a general rule. Root locus always starts from the pole when k equal to 0 and always ends at the 0 when k equal to infinity. Okay, if we don't see a 0, there is no 0, we imagine there is 0 at infinity. So, for these 2 poles, one of them must start from here when k equal to 0, and it will break away and go to another 0 at infinity on the top, and symmetrically, the other one will go down. You got it? Now, how to know where it's going, this way or the other way? We need what? The next step, we need to draw the asymptotes. We need to draw the asymptotes. So for the asymptotes, you need 2 things. You need 2 things for the asymptote. You need the angle for the asymptote, and you need the center of gravity of the asymptote. The angle, there is a rule, we talked about it. It's going to be plus or minus 2 small k, this is an integer, not the controller, plus 1 times 180 degrees divided by the number of poles minus the number of zeros. Okay, so for theta, let me write it here, theta 0, it will be plus or minus 0 plus 1, 180 degrees divided by number of poles minus number of zeros, which is going to be plus or minus, I think, 60 degrees, right? Yes. For theta 1 integer, okay, where let me write it here, k, small k is an integer, 0, 1, 2, and so on. So theta 1 will be plus or minus 1 or 2, sorry, plus 1 times 180 degrees over 3 minus 1 plus or minus 180 degrees. Theta 2 plus or minus, how much theta 2? 2 times 2, 4 plus 1 times 180 degrees divided by 3 minus 1 equal to, I think it's going to be 300 degrees. Yes. Now, plus 300 degrees is the same as minus 60. And minus 300 is the same as plus 60. So you're going to repeat the same angles from this point and on. So what you're going to do, you're going to stop. When you start repeating, when you start repeating the same angles, you need to stop, okay? خلاص. Everything will be the same. So these are the angles that you see, all right? All right. Now we know the angles. We need the center of gravity for the asymptotes. Center of gravity, let me call it sigma A. This is the point on the real axis that will determine the center of gravity for the asymptote. It's going to be the summation of the poles minus the summation of the zeros divided by the number of poles minus number of zeros. Okay. Let me divide this. Oh, sorry, it's not nice. I will divide it later. Okay, so it's going to be how much? Summation of poles, we have 0. We have minus 1. So it's going to be, let me write it here. We have 0, we have minus 1, we have minus 2, and we have no zeros. Divide by number of poles minus number of zeros. It's going to be how much? It's going to be minus 1. This is minus 3 over 3. It's going to be minus 1. So sigma A is minus 1. All right. How are we going to draw this? We go to the... let me use a different color. Let me use a green. We go to minus 1. So this is minus 1. So here, this point will be sigma A. Now, this is a coincidence, okay? This is a coincidence that the sigma A, the asymptote center of gravity, is on the pole, minus 1. It's not always like that, okay? They do not depend on each other, okay? These are different, all right? So from here, we will draw the asymptotes. We have one asymptote plus 60. Is this like 60? No, it's like 45. Let me erase it. Okay. Okay, let me draw it again. Like 60. This is more like 60. Plus 60. Minus 60. Okay. And plus or minus 180. This is here. Right? Now clearly plus or minus 180 is the asymptote of which branch for this branch, right? So we don't need it. Okay. So this is plus 60. This is minus 60 degrees. All right. All right. Very nice. Now, where is the breakaway point for the other two branches? Okay. There is a rule in the book and also in the notes. Okay. If you want to find it precisely, where is the breakaway point for the branch. But for approximation, not to waste your time, and the error will be very small, there is also another general rule. The breakaway point will be always between two adjacent poles. So where are the two adjacent poles in this example? We have these two poles and these two poles, right? Between 0, minus 1, or minus 1 and minus 2. Now, which one you're going to pick? I'm going to pick this one. Why? Because between minus 1 and minus 2, there is no root locus. So how are you going to break away for a branch where there is no root locus? So the breakaway point must be between 0 and minus 1. Okay? So the breakaway point must be between 0 and minus 1. So I'm going to estimate, as an estimation, I'm going to estimate in the middle. The breakaway point is in the middle. Okay? So one branch will start from this pole with k equal to 0, and then it will go to the left as you increase k, and then it will go to the breakaway point as you increase k further, and it will break away like 90 degrees. Then it will go close to the asymptote, but it will never cross the asymptote. And then it will go alongside the asymptote, just like that. The other branch will start from this pole when k equal to 0. And then as you increase k, it will go to the left. Then it will go to the same breakaway point and symmetrically it will follow this path, which is symmetrical to the above root locus. So you can see the root locus always symmetrical. The real axis is always like a mirror. What you see in the top, you will see in the bottom. Why? Because if you have a root locus, if you have a root here of the characteristic equation and it's a complex number, then its complex conjugate also another root, right? You see? All right. So let me write what I did here. Let me write it here. This is a number, step number 5, 6. This is 5 or 6? 4, 5. Yeah, this is number 5. Sorry. Okay. So number 5. Number 6. The breakaway point of root locus on the real axis is between two adjacent poles, which are P1 and P2 at minus 0.5. Okay, estimation, huh? This is an estimation. Minus 0.5. It's an estimate, okay? If you want to find it precisely, there is a rule here. You can see it here to find it precisely, but I'm not going to use it, okay? Because the error will be very small and we don't have much time to do that, okay? All right, so this point is minus 0.5. This point. Okay, minus 0.5. Good. All right. What's left? خلاص, we're done. This is the root locus of your system. Okay. So we did number 1. We did it. Draw the root locus. We draw the root locus. Okay. Next, we want to specify K range for stability. Now we come to the analysis and understanding. Okay. Now we come to the analysis and let me use another color. Okay, which one we're going to use? Let me use K, black, just hide. Now, what is the region of stability? What does this mean, this root locus means? This is the real axis, this is the imaginary axis. Any root on this region must be what? Stable. Any root in this region will be on, let me write it below because I'm going to use this one. It will be on stable. How do I know this? How do I know this? Because this is the real part. When it's negative, then the system will be stable. When the imaginary part is positive, then it's going to be unstable. So to understand, let me show you again. What is this? What does this mean? For this control system, how many root locus you will always have? You will always have 3. How do I know? If you solve 1 plus open loop transfer function, if you solve 1 plus, why it's not working? Okay, sorry. Okay, let me write it again. 1 plus open loop transfer function. How many roots you will have always? Always you will have 3 roots. 3 roots. You can check that later. Next we will do that. You will always have 3 roots. But every time you change K, you will have 3 roots. So when K equal to 0, what are the roots of the characteristic equation? It will be the pool. here, and here, and here. These are the three roots. Okay. So when k equal to 0, let me use another color. Or I can use this one. No. Green, we already used the green. Blue, we already used blue. Purple, let's use purple. When k equal to 0, you are here. And here. And here also. Got it? So when k equal to 0, you are on this pole, and this pole, and this pole. Three roots of the characteristic equation. Okay? When k equal to 1, what will happen to this root? It will go to the left. This one. Let me use the laser. When k equal to 1, this root will move to the left here, somewhere here. When k equal to 1, also this root will move to the left. How do I know? Because this root locus is my guidance. It's like the map or road map for your car, for example. So let's assume these routes or these poles or the routes are the car. And the root locus is like the road map. Okay, it will show you the direction for the car, where it's going, or the route. So when k equal to 0, you are here, you are here, you are here. Always we have three routes, or cars, if you want to imagine. Now when k equal to 1, this car or this route will move to the left. When k equal to 1, this one will go to the left. This one will go to the right. Okay, this one will go to the right. All right. When k equal to 10, this one always will go to the left. How do I know? Because this root locus showing me always to the left. This one, if you increase k to 10, maybe it will go to the and it will go up. This one will move to the right and it will go down. You got it? All right. Okay, what about if you increase k to infinity? When you increase k to infinity, okay, this root will go to, when k equal to infinity, it will go to 0 at infinity. We call it 0 at infinity. Okay. Zero at infinity. Okay. When k equal to infinity, it will go to 0 at infinity. In fact, the root locus always starts at the pole when k equal to 0 and always ends at the 0 when k equal to infinity. But we do not have 0 here, so we will imagine there is far away 0. We will call it 0 at infinity. Okay. What about this root when k equal to infinity? When k equal to infinity, okay, it will go to another 0 at infinity. We call it 0 at infinity. This one, same thing. When k equal to infinity, it will go to another 0 at infinity. So we will imagine there is a 0 far away there. We call it 0 at infinity. In other words, what if we have a real 0 here? Like at -3, we have a 0, -3. What will happen to this root locus? It will stop here when k equal to infinity. You got it? I hope this is clear. All right. Now, how are we going to design k range for stability? After we understand this root locus, how are we going to design k range for stability? We're going to check each root locus or each branch. This branch will be always stable. So k here is not limited. K range is not limited. Whether k0 or large number, the root will be always stable, right? The root will be always stable because it's going to be a negative real part. What about this root or this branch? This branch, for low values of k, it will be stable. But when we reach this point, this is going to be the limit. After this point, the root will become unstable. Okay. What about this one? Same thing here. So we need to define the limit. This is going to be my limit. How much k here This is going to be the limit. Okay? And how much omega? This value. Because we know sigma. Sigma here will be 0. So this is going to be critically stable. Same thing here, K. It's going to be the same K. How much K? This is going to be my limit. And how much omega? Which will be the negative omega here. So this is our next job. How to find the K range? We need to find these 2 points. If you find these 2 points, you will find the limit. You will find the range from 0 to this point. You got it? So how are we going to find this point? This is what we're going to do next. Okay. What is the K range for stability? Let me remind you. You need to solve this equation. 1 plus the open loop transfer function, which is what? What is the open loop transfer function? It is K S plus 1 S plus 2 equal to 0. So how are you going to solve this one? We need to solve for the roots at these 2 points, huh? So I'm going to plug in here that sigma equal to 0. That's all. This is what I'm going to do next. So I'm going to need to simplify this. This is going to be S plus 1, S plus 2, plus K equal to 0. This is going to be what? S squared plus 2S or 3S plus 2 plus K equal to 0. All right. And this gonna be S to the power 3 plus 3S squared plus 2S plus K equal to 0. This is my characteristic equation. 1 plus K. This is the same, huh? Same. All right, what we're going to do now, we're going to substitute S equal to, remember what is S? Sigma plus J omega, right? Right. How much omega here at this axis? Omega equal to 0. So you're going to substitute omega equal to 0. Substitute only J omega. So this is going to be J omega cubed plus what? 3 J omega. Okay, let me erase this. What's again? 3 J omega plus 2 J omega plus K capital equal to 0. Okay, need to simplify. This is going to be minus J omega cubed plus or minus 3 omega square plus J2 omega plus K equal to 0. Collect all the imaginary together and the real part together. This is the real part. It's going to be K minus 3 omega squared plus J 2 omega minus omega cubed, right? Equal to 0. Now, this is true. This equation is true as long as the real part equal to 0 and the imaginary part is also equal to 0 at the same time, right? So from here, K minus 3 omega squared must be equal to 0. And 2 omega minus omega cubed must be equal to 0. So we have 2 algebraic equations. How many unknowns? 2 unknowns. Can you solve for K and omega? The answer is yes. So let's solve for omega from here. This is going to be omega 2 minus omega squared equal to 0. So either omega will be equal to 0 or 2 minus omega squared equal to 0, and here will be omega equal to plus or minus how much? It's going to be, this is omega squared, plus or minus square root of 2. Right? So, if omega, when omega equal to 0, from this equation, this k means or must be equal to 0, right? Right? If omega equal to plus or minus square root of 2, how much k will be? 3 times 2 equal to 6. Okay? When omega equal to 0, when omega equal to 0, k equal to 0. Where is it? When omega, this omega equal to 0, k equal to 0, we know this already, right? From here, which is at this pool. Just for your information. When omega plus or minus 2, which are these 2 points, here one, so this is omega plus 2, plus, sorry, square root of 2. This will be how much? 6. This one, also same thing, but negative square root of 2. How do I know this? From here, from this one. So k range, therefore, k range for stability is from 0 to 6. خلاص? From 0 to 6. Okay? All right? From 0 to 6. So 0 is okay. And 6 also okay. This is the limit. Got it? And this is the solution. The total solution. All right? So when k equal to 0, the system is stable, okay? This one's stable, this one's stable, this one critically stable. So the whole system will become critically stable. When k equal to 1, this one's stable, this one's stable, this one also stable. When k equal to 6, this root will go to here, and this root will go to here, and this root always go to the left. It will become critically stable, 6. That's okay. 6.1, no, it will go here. One root, at least one root will become unstable. So the whole system will become unstable. Also this one will become unstable. K equal to 10, this root will go in here, also still unstable, not good. This one's stable, but doesn't matter. If you have one unstable root, the whole system will become unstable. I hope this is clear. Okay, you need to solve more examples, inshallah, and it will be much better for understanding. All right. Thank you for listening, inshallah. See you